We will take one of an example for the structure of an compilation process. See here, this is one of the example problem to determine the phases of compilation. To tell the phases of compilation, I'll explain with the example. So see here, sum equal to old sum plus rate into 15. This is an input, means this is an source program we have given to the system. Okay, so this one is an input. So we have to convert this input into the machine code. So to convert the machine high level language to the machine language, what is the phases we have to complete? We have to complete 6 phases of compilation process. So we will see each step how the compilation works. Okay, first this is an source program. From this source program, first we are taking the first phase, that is an lexical analyzer. This is the first phase of compilation process. So in this first phase of compilation process, what we will do, we have already seen the first video. That is, in this first phase compiler, we will take the characters as an input and we will convert these inputs in the form of lexemes. So that lexemes we are calling it as tokens. So first we will convert those input. To convert those inputs into lexemes, suppose I am giving an identifiers for this. This is the first identifier, second identifier, third identifier and fourth identifier. I am assuming like that. Okay, I'll write here ID1, ID2 plus ID3 into ID4. So in the place of this original source program, I am converting, means I am writing in the place of sum, I am writing ID1. In the place of old sum, I am writing ID2. In the place of rate, I am writing ID3. In the place of 50, that is in the form of value, I am writing ID4. Okay. So we will see we are calling it as token. Okay. What is the output for the lexical analyzer? Token we are getting. From that token will be acting as an input to the next phase, that is syntax analyzer. So what this phase will do means, so we have already seen the definition of syntax analysis. What it will do, it will take the tokens from the previous steps and it is going to generate the parse tree. Okay, so we have to take this input and we have to convert, for this input we have to convert this input into parse tree. So look here, I will write how to write an parse tree. Okay, first this is an one expression and this is an one expression, because this is an left side and this completely is for right side. So first take an operators. So as an root node you have to take the operators, as the child nodes you have to take this identifiers. Okay, first I am taking the equal to symbol. Why? Because this is separation of ID1. This is the separation symbol for the left side and right side. So first root node you have to take equal to. For one node will be having the left side and for the same node we are having the right side also. Okay, for right side what we are having ID1, and what is the left side we are getting, we are having total this. So what we have to write in the root node places, you have to write only the operators. So what is the next operator after the equal to is plus. So you have to write plus here. After writing the plus here, for plus this will be the right side and this will be the next side. So see here ID2 and this side I have to write into. Why? Because we have to use only the operators here. So next in this we are writing ID3 and this in this side we are getting ID4. So look at here, first ID1 equal to ID2 plus here plus, next id3 here I am writing, means we have to write for this complete expression I have written this one, for this complete expression I have written this one totally, for this complete expression I have written this total. Okay, so see here once again I will explain. For equal to I have written id1, for plus I have written id2, and plus into I have written id3 and id4. So this is how you have to generate the parts tree. This we are calling it as parts tree. So remember that all the operators should be the root node, remaining you have to write in the child nodes. Okay, this is the only concept you have to write in the semantic analysis. So this semantics analysis, what we are getting the output as a parts tree, this will be the input for the semantic analyzer. So next method is, next phase is semantic analyzer. So what we will do in the semantic analyzer, this is the third phase of compilation process. It is going to check, or it is going to have all the track record of identifiers, expressions. We are having the tracking in this semantic analysis. What is the output we are getting in this semantic analyzer? Annotated tree syntax we are getting as an output. So in this program we will see how to generate the semantic analyzer. So see here, first same like parts tree, same like parts tree right here, but only difference between this parts tree and annotated tree means in the place of id4, we are having the value. Is it right? So these are all the identifiers we are assuming, but this is an value. So this value we have to represent same like this only, because in this replacing of this value we can't use any other value. So we have to use only the 50. So I will use here, see. So take the same diagram, plus equal to this side id1, next plus id2, next into symbol, next id3, in this place and this place, at this id4 place we have to write 50, the value we have to write here. Why we are writing here only that value means, what is the problem? id1 equal to id2 plus id3 into 50. In the question they have given in the last place, so I have written in this place 50. Okay, this is an semantic analyzer. This is an annotated tree syntax. So next we will see what is mean by the next phase, that is intermediate code generator. We will take this annotated tree as an input in the intermediate code generator. So what we will do means, first take one temporary variable, that is temp1. So temp1 is an temporary variable. It is going to recognize this value. This 50 we have written. No? This is also called as interval. Introrial. So we have to write here introrial. What is the value of there? 50. So in the temporary variable I have stored interval 50 first. After storing, why I have shared first means, here from here I am starting to store the variable. I have taken the temporary variable, that is temp1. Take another temp variable, that is temp2. In this temp2, see here, id3 into 50. So this is a question, right? id3 into 50. So what we have to store in the temporary variable means id3 into 50. So we have already stored the 50 variable. Then what we have to do next, in the form of here, see here, we have stored this 50 in the temp1 already. So for this we have to write the id3 into 50, right? So we have to take another temporary variable, that is temp2 equal to id3 into temp1. What is the temp1? Int L'Oreal 50. So this value will be stored in temp1. So id3 into temp1 will give the result and it will be stored in the temp2. Okay. Next, take a next one. Temp3 is equal to temp2 plus temp2, means id3 into temp1 is stored in temp2. So id2 plus temp2 gives, and these output will be stored in the temp3. Okay, see here, id2 plus this total is temp1. So what we have to write here, id2 plus temp2, that will be stored in the temp3 variable. Okay. Next, coming to last, we are having only the temp3, that is id1 will be stored in a temp3 variable. See here, in the temp3 that will be stored in the id1. Okay, this is an intermediate code generator. We have stored all the IDs in a temporary variables. So what the role of the intermediate code generator is, it is going to convert the high level language to the machine understandable language. It acts as an intermediator between the high level and also the machine language. Next phase we will see what is mean by the code optimization. What is the role of code optimization? It is going to remove all the unnecessary errors in our code, and it is going to give the optimized output to the next phase. Okay, we will see how the optimization going to work. Take the temp1 equal to id3 into 50.0 and id1 equal to id2 plus temp1. So what is mean by temp1 means, in the temp1 it is going to store id3 into 50. I'll show you here. So see here, in the temporary variable in the code optimization, it is going to convert this whole. So this is a lengthy process we have generated in the intermediate code generator. So this is a code what we have produced. So this produced code we have to be optimized, means we have to reduce the number of steps in the code optimization. So how we are writing is temp1 equal to id3 into 50. So in this we are taking this as an temp1, and we are writing id1 equal to id2 plus this temp1. Okay, in the two steps we can complete the code optimization technique. See here, id1 equal to id2 plus this total we are calling it as temp1. So we can store in the two steps. So but in an intermediate code generator we have stored each and everything in a single statement line. So extension to the intermediate code generator is an code optimization. So what we have written, temp1 equal to id3 into 50.0 and id1 equal to id2 plus temp1. Okay, so code optimization can take float values also. Okay, remember this one. So point in the sense float. This float values can also be used in the code optimization. See here, in the two steps we have written the source program. Okay, we have optimized the code to the 2 steps. In the last final one is an code optimization, code generation. Sixth phase in an compilation, that is the code generation. So what we will do in the code generation means, so see here, move f, that is move float id 3 comma r2. R2 is nothing but the registers here. Move is nothing but move the shift IDs to that particular register. Okay, move f id 3 comma r2. Next, mulf is nothing but multiply. I'll tell you after writing 50.0 comma r2. First I'll complete writing, then I'll explain. Move f id2 comma r2. Next, add f r2 comma r1. Next, move f r1 register to id1. So this is an code generator, how we are writing. So I'll explain. First I have moved id3 into r2 register. Next I have multiplied for R2 register with 50. Okay. What is the code for us? See here, I'll write here. ID1 plus ID2 into ID3 50. This is our parts tree. For this parts tree we are writing this. First ID3 will be stored in an R2. Okay, first in this ID3 will be stored in the R2 register. Then MUL is nothing but multiply. So these two, for this two we have to write the multiplication. So that's why I am writing here multiply 50 in R2. Okay, why? Because in R2 we are already having ID3. We have moved ID3 into R2. So again we need not to give the ID3. We can just simply give the float value, that is 50.0. This hash is nothing but the real type. This hash we can call it as real type. After this, move f id2 to r2. So this all we have moved to the r2. Next id2 we are moving to r2 register. Okay, this completely stored in the R2 register. Then add R2 and R1. So consider we are calling it as R2, and this we are calling it as R1. So we are adding this R1 and R2. After finishing this single steps, we are taking this whole step in an R1. This one we are storing in already R2. We are just assuming this total consists in an R1 sorry. Okay, so move R1 to the ID1. So in the ID1 I have moved to the R1. Okay, this is an final step of code generation. After getting all this finishing these steps, we are getting the target program. This is the final step of compilation, phases of compilation.